This video explains heritability and selection, addressing the following points. When will selection result in a breeding gain? It will deal with narrow sense heritability, the selection differential, the selection response, and last, the relationship between these variables. Heritability is an important question, often posed by plant and animal breeders who are faced with the task of improving continuously varying traits such as yield. Take a plant population whose value for a given trait displays a Gaussian distribution. Can we breed for better plants by selecting and breeding individuals at the edge of the distribution? The answer is that it depends on what is the nature of your population. This was demonstrated in two striking experiments carried out about 100 years ago. In the first, a scientist called Johansen bred a pure line of bean. When the single seed weight of the line was measured, it fit a normal distribution. Johansen decided to select for different seed size. Before we go any further, let's learn an important term. The difference between an individual selected for breeding and the mean of the population from which it comes is called the selection differential, or S. Johansen selected seed of different weights, such as small, medium, and large, and asked whether the progeny of these plants produced similar seeds. He found that if he started with a pure line, selecting a small or a large seed had no effect on the size of the next generation. This makes sense because we now understand that the variation displayed within a pure line is not genetic, but due to environmental effects. When is selection effective? Two conditions must be fulfilled. 1. The starting population must display genetic variation. 2. Genetic variation must be additive. Additive means that each allele affects phenotype in a way that can be calculated by simple addition. For example, big T has a phenotypic value of 5, little t of 2, and therefore the genotype of big T, little t in heterozygote is equal to 7. If we know what fraction of total phenotypic variance is due to additive genetic variance, we can derive narrow sense heritability according to this formula: lowercase h square equal VA over VP. This is important because h square, lowercase h, predicts our breeding gain. The higher the h square of a population, the more predictable is the response to selection. We will use corolla length in Nicotiana to explore this concept. In 1916, East published the analysis of a continuously variable trait, corolla length in Nicotiana. East started with inbred varieties. This table displays his results. Columns show counts of individuals with a given corolla size, shown as increasing from left to right. Rows are the progressive generations, from parents on the top to F5 at the bottom. The size of each generation parent is shown in the yellow column. If this looks confusing, fear not, it will become clearer as we go on. Individuals of each purebred parental variety are distributed around the mean. One variety, called P1, had a short corolla of 40 mm in average. The other had a long corolla with a mean of 90 mm. Their F1 and F2 displayed intermediate values with a mean around 70 mm. The F2 is much more variable than the F1, indicating that there is a strong genetic component in this system. East selected the extremes in the F2 and selfed them. He made rapid progress. For example, he selected an F2 individual with a corolla 50 mm long and got an F3 progeny from this individual with a mean of 50 mm. He then selected an F3 with a value of 44 mm and got an F4 mean at 46 millimeter. He continued selection, and by the F5, the progeny displayed a distribution close to that of the parent with the short corolla. In other words, he was very successful, indicating that the trait of interest had an additive genetic basis. Now let's consider the selection differential in the F2 to F3 selection case. It was 20 millimeter. His selection response was 20 millimeter. We can calculate narrow sense heritability in this system by using the following formula. H squared equal R over S, which is equal to 1. Now there is a problem with this estimate. It is based only on a single case. A more reliable way to estimate narrow sense heritability is to use the data in many parental filial combinations. The graphs plot the mean of the parents on the x-axis versus the progeny on the y-axis. The regression line describes the relationship between the two variables. Narrow sense heritability is equal to the slope of the line. In this case, is equal to 0.5. In the second plot, it is obvious that the trait value of parents and progeny is not correlated. The slope of the regression line is equal to 0, and so is narrow sense heritability. In summary, we can derive narrow sense heritability by comparing the phenotype of parents and progeny in a genetically variable population. Importantly, once we know narrow sense heritability, we can calculate the expected response from a given selection differential.